Hey everyone, and welcome to The Explainer. Today, we're diving into the internet's ultimate traffic cops, load balancers, and network defense systems. Imagine a massive, chaotic city intersection where a highly trained officer isn't just directing thousands of commuters with perfect efficiency, but is actually actively stopping malicious vehicles trying to cause a massive pileup. Well, that is exactly what modern network architecture does every single second. And today, we're going to unpack exactly how all of that works under the hood.
Now, you might be wondering why getting this right is so absolutely crucial. Well, look at this number, $1.9 million. According to recent data, that's how much a severe network outage can cost an organization in just one single hour. Mastering this network architecture isn't just some boring IT checkbox, it's quite literally a fundamental requirement to keep your business alive. Because the second your network goes down, you're instantly losing valuable customers, critical revenue, and a whole lot of hard-earned reputation.
So, here is our game plan for today. We'll start with the basics of load balancing, then move into smart traffic routing algorithms, master session persistence, understand DDoS attacks, and finally, look at exactly how we defend against those specific threats. Let's jump right in. Section 1. The basics of load balancing. Okay, so breaking this down, there are basically three main types of load balancers: application, network, and gateway. And they actually operate across completely different OSI layers. An application load balancer, or ALB, works up at layer 7. It handles HTTP and gRPC protocols and actually terminates the client connection to act as a proxy. Then you've got your network load balancer, or NLB. That operates down at layer 4, dealing with TCP and UDP protocols for extreme high performance, super low latency needs. And finally, a gateway load balancer sits across layers 3 and 7. It's basically a transparent entry point that forwards traffic without terminating the flow at all, which is absolutely perfect for deploying virtual security appliances. The difference between layer 4 and layer 7 is honestly fascinating when you get into the mechanics. Think of layer 4 as a lightning-fast, totally blind mail sorter. It just looks at network info, like IP addresses and ports, and forwards the packet on its way without ever bothering to look inside the envelope. Layer 7, on the other hand, is way smarter. It provides intelligent, content-aware routing. It literally decrypts the traffic, inspects the HTTP headers or the message content, and makes complex routing decisions based on exactly what the user's application is asking for. Moving right along to Section 2, Smart Traffic Routing Algorithms. So, how do these balancers actually decide who goes where? It's really an architectural choice between the simplicity of a static system and the efficiency of a dynamic one. A static, round-robin approach just deals traffic sequentially: server A, then server B, then server C. It's incredibly easy to set up, but it's completely blind to how busy those individual servers actually are. Conversely, least connections is a dynamic approach. It actively monitors the network and routes the very next incoming request to the server with the fewest active connections. This is way superior if you're managing uneven workloads where some requests just naturally take a lot longer to process than others. But here's a big question. What happens in a massive cloud environment when a node suddenly crashes, or you need to dynamically scale up? With traditional algorithms, changing your server count means you have to mathematically remap almost every single request, and that causes immediate chaos. To solve this, engineers use something called consistent hashing. It creates this virtual hash ring. Both your backend servers and your incoming requests get mapped onto this ring, and an incoming request just travels along the circle until it bumps into the closest available server. And the architectural benefits of this ring system are profound. If you add or remove a node, only a tiny, localized fraction of those requests needs to be remapped to a new neighbor. This preserves a massive amount of your cache data, drastically boosts your scalability, and prevents what we call a thundering herd of uncached requests from suddenly breaking through and totally overwhelming your backend databases all at once. All right, Section 3, Mastering Session Persistence. Picture this. You're adding items to a shopping cart on a complex SaaS app. You click to the next page and suddenly, you lose all your progress. Why? Because the load balancer blindly routed your second request to a completely different server. To fix that, architects use specific methods of session persistence. Whether you're relying on cookie-based tracking, IP-based affinity, URL rewriting, SSL session IDs, or injecting custom headers, all these methods do one thing. They ensure a user's session becomes sticky. Their sequential requests will consistently reach the exact same server that holds their local state data. Now, while sticky sessions are awesome for continuity, they do lock traffic to specific nodes, which inherently makes your whole system harder to scale. The modern alternative? A stateless architecture. In this model, servers don't store session data locally at all. Instead, each individual request carries all the info it needs, or the system relies on a centralized distributed cache like Redis. Sticky sessions are definitely easier if you're just lifting and shifting legacy apps, but going stateless allows your systems to scale horizontally with way more efficiency. Okay, so we've built a super robust, perfectly balanced network. But what happens when the traffic hitting that network isn't trying to use the app, but is actively trying to break it?
That brings us to Section 4, Understanding DDoS Attacks.
So in a standard distributed denial of service or DDoS attack, a bad actor coordinates a massive botnet and just floods a targeted victim with requests. It is literally an artificial, malicious traffic jam designed for one single purpose: to exhaust the target's infrastructure and completely block legitimate traffic from getting through.
And the sheer scale of what modern network defenders are up against is honestly staggering. Recent threat reports show hyper-volumetric attacks hitting a massive 6.5 terabytes per second. Traditional on-premise server farms just cannot absorb bandwidth spikes of that magnitude. They get completely wiped out in a matter of seconds. Attackers generally categorize their strikes into 3 distinct buckets. First, volumetric attacks. These target sheer network capacity, trying to consume all your bandwidth and saturate the pipes. Second, protocol attacks. These exploit transport layer vulnerabilities to completely exhaust the state tables of your firewalls and load balancers. And finally, application layer attacks. These directly target the web server's application logic, silently overwhelming the server with what look like legitimate HTTP requests until the underlying processing power just crashes. Let's look at how we fight back in Section 5, Defending Against DDoS Threats. Organizations can effectively lock down their networks by engineering a defense across 5 critical steps. Number 1, tailor your approach based on the resource. Use reverse proxies and robust web application firewalls to obscure your server's true IP addresses. Number 2, prioritize expansive capacity and a lightning-fast time to mitigation by routing traffic through distributed cloud-based scrubbing centers. Number 3, implement an always-on protection model so traffic is continuously inspected without ever needing someone to manually react. Number 4, ensure your security doesn't add unwanted latency, because legit users still demand instantaneous load times. And number 5, leverage intelligent, continuous traffic analysis to spot behavioral anomalies and stay one step ahead of those zero-day attack vectors. Which leaves us with this final thought. Modern infrastructure requires absolute, constant vigilance. As cyber threats get wildly more complex and user expectations for zero-latency speed skyrocket, how are you balancing lightning-fast performance with impenetrable security in your own network architecture? It's a tough puzzle to solve. Take a hard look at your systems and ask yourself if you're truly prepared for both the good traffic and the bad. Thanks for joining me for this explainer, and as always, keep learning.